This is the 5-5 notes for Precalculus 2. This section is a very important one, especially for students that are moving on to calculus. You will be asked to solve trig equations in those classes from here on out, so take note of that when we're going through it. So what is a trig equation? So it makes sense. It's basically any equation that has a trig function in it. So our first equation up at the top here, you'll see that the sine of x is equal to 1/2. Basically, you would be asked to solve this for all possible values of x. Now, take note here that when you usually solve equations in algebra and even some of the things you've done so far in Precalc 1 and here in this class, normally you have a finite number of solutions, but realize that a sine graph basically does this, right? It goes on forever. So that means every single time it comes up to 1/2 on the graph, you have a new answer. So literally, if we didn't cap the range of possible values, then this problem here would actually have an infinite number of answers. Basically, anywhere it comes up to 1/2 on that entire spectrum that it goes by. But for the purposes of our class, we're going to stick just to the spectrum or range 0 to 2 pi. Now note, I did put a bracket on this side and a parenthesis on this side. Why is that? Because 0 and 2 pi are coterminal angles, which means taking a trig function value for them creates the same answer. So it's redundant to use both of them. So what we do is we remove 2 pi from the scenario and just stick with 0 in terms of our possible results. So let's look at sort of this scenario more in depth. So it says we can clearly use our knowledge of the unit circle in quadrant 1 to come to the conclusion that the sine of what is 1/2. Okay, so if we're in quadrant 1 over here, right, and we want the sine of something to be 1/2, then we want its y coordinate to be 1/2. Well, you guys know that in order for that to happen, the x coordinate has to be √3/2, and that means we are dealing with the angle pi over 6, which means the sine of pi over 6 is indeed 1/2. Now note, that doesn't mean that the only answer to the problem is pi over 6. Sometimes it might be, but in most cases it's not. So in this scenario, there is another member of the family, pi over 6 family, that has an answer of 1/2 if you take its sine. So note, we're only going from 0 to 2 pi. Now 0 to 2 pi is one full rotation around the circle. So what we need to do is we need to look for another quadrant where the sine of some pi over 6 family is 1/2. Well, how would we find that? Well, that should be pretty straightforward. Why? Because again, in the quadrants, the only place where you're going to get a positive solution is in quadrant 1 and sine in quadrant 2. So all we have to do is find the pi over 6 family in the second quadrant, which is going to be 5 pi over 6. So just to reiterate, it says, starting here, if we consider the unit circle, we also know of one other member of the pi over 6 family that creates a positive solution for sine, namely 5 pi over 6 in quadrant 2. So what does that mean? It says, therefore, the solutions to the equation sine x equals 1/2 on the interval 0 to 2 pi, only including 0, would be pi over 6 and 5 pi over 6. Okay, so you would literally write, by the way, you would write x equals pi over 6 comma 5 pi over 6 as your solutions. Okay, that would be the result. Now note, if we went beyond 2 pi, then there would be an infinite amount of solutions. Every single time you came back around into the first and second quadrant, you would add a solution and so forth as you went, because the sine graph goes on forever. We're not going to do that in this class, so you don't have to worry about that, but from this scenario, we basically would get pi over 6 and 5 pi over 6 as the results. Okay, I just want to add to this scenario. So just a lot of times students will struggle a little bit with the differences between inverse trig functions and solving a trig equation. Why? Because it's tangentially, meaning it's similar in concept, because yes, you're working backwards from the ratio to the angle, right? That's the idea. You do the same thing in both. But realize whenever we have any type of setup for inverse trig functions, remember that cosine was always on the top and sine and tangent were on the right. So because we cut off those graphs to make them functions, we limit the results on what they can be. So when you take the inverse of something, there's only one answer. When you solve an equation like what's going on over here, you can get multiple answers that can be in any quadrant, and specifically for us, from 0 to 2 pi. So just take that in mind in case you get confused between inverses and solving trig equations. Okay, so next, let's say we have tangent x is equal to 1. So just a note real quick. So this right here is a typo, so just remove this. I'll remove it on the actual copy when I get a chance. So let's say you have tangent of x is equal to 1. So again, what are we trying to do? We're trying to find, with our knowledge of the unit circle, when the tangent of x is equal to 1. Well, let's start in quadrant 1. Well, in quadrant 1, we have to figure out when y over x is 1. Well, that only occurs when the first and second coordinate, members of the coordinate, are the same, and that will only occur at the pi over 4 family. So we know that the tangent of pi over 4 is equal to 1. But here's the issue. Again, that is one of the solutions. Now the question is there any other quadrant where we get a positive 1 from the tangent of a pi over 4 family? Well, if you look at all students take calculus, you look at this and go, hey, we also have a positive result in quadrant 3. So what do we have to do is we have to find the pi over 4 family in quadrant 3. Well, what is that? We'll start here again. So if we consider the unit circle, we also know of one other member of the pi over 4 family that creates a positive solution for tangent, namely 5 pi over 4 in quadrant 3. Okay, which means if we solve for the solutions of tangent x equals 1 from 0 to 2 pi, then we are going to get pi over 4, our original answer, and 5 pi over 4, our second answer, as our solution. So if you were to be doing an actual problem, you would be getting this as your result. So again, multiple solutions. Now, does that mean there's always going to be 2? Not necessarily, and we'll talk about that in a second. But the key is it is working backwards, and you want to find the quadrants in which this occurs in these scenarios. Okay, so let's do an example. So one of the things about trig equations is they're not always in the form you want them to be. So when we did these guys up here, this guy and this guy, you'll see that sine x and tangent x were already isolated on the left side. That will always not be the case. So, for example, in problem number 1, we have 5 cosine and 3 cosine. Remember, this is not the same as cosine 5x and cosine 3x. These are two totally different things. And by the way, they wouldn't be like terms either, whereas these would. I have 5 cosines and 3 cosines, which means I should be able to subtract 3 cosine from both sides and get 2 cosine remaining on the left. Remember to bring the negative with the negative root 3 on the right. So what am I trying to do here? I am trying to isolate cosine x on the left-hand side of this equation. So clearly, I need to divide by 2 and get negative root 3 over 2. Okay, so now you'll see that this is in the exact form that we needed in order to solve the equation. So what is the point of this? We need to find solutions to in terms of special families of radian values that we know, where remember, cosine is the x coordinate, right, is root 3 over 2. So specifically negative root 3 over 2. But just generally, if we have a x coordinate of root 3 over 2, that means that our y coordinate is a half, and we know this occurs at the pi over 6 families. But we need it to be negative. So again, what do? We go to our All Students Take Calculus, and we find the two quadrants where cosine must be negative. Well, where is it positive? It is positive here and here, which means we want these two quadrants to be where the solutions of this problem will lay. So what do? We find the pi over 6 family answers in those two quadrants. What are they? We have, remember, this is 6 pi over 6 right here. So if we go this way 1, we get a pi over 6, we get 5 pi over 6. This way is 7 pi over 6. So that means our solutions are 5 pi over 6 and 7 pi over 6. Now note, realize that I didn't do any fancy algebra here, nor did I do the inverse. Now, a lot of students will get to this step right here, and they'll be like, oh, the only way I can find the angle is to find the inverse. Well, if it says to solve the equation, never use the inverse in this scenario, because if you solve that equation, you would get, the only answer you would get is 5 pi over 6, because you would be in the top over here. But if you're solving an equation, you're going to get both answers, 5 pi over 6 and 7 pi over 6. So as I stated in the beginning, this is a very important section. I do find that students struggle with this section just for whatever reason, probably because maybe their understanding of previous material isn't quite where it needs to be, but because of the importance of this section, we're going to do a lot of examples. So if you go through it, you'll see that we're going to do, right now, we're going to do 5 more examples, 2 through 6. So hopefully by the end of this, you should be really understanding what you're supposed to be doing. So looking at 2, we need to solve the equation tangent x is minus root 3 is equal to 0. So again, we need to isolate tangent x. So how do we do that? Very clearly by adding root 3 to both sides. So if we do that, we're going to get tangent x equals root 3, and we officially have exactly what we need for the isolation of this problem. Now, the hard part is realizing that we somehow have to find the tangent, which is y over x, so that it's root 3. Now, realize we need y over x to be root 3, or in other words, root 3 over 1. So hopefully by now, based on your understanding of inverse trig functions, that you realize that that is the same as root 3 over 2 and 1 over 2. So that means our coordinate is x is 1/2 and y is root 3 over 2, which occurs at any pi over 3 family, or any variation of that occurs at a pi over 3 family. So you'll notice that we're looking for a positive root 3, which means we need to go into our All Students Take Calculus in our quadrants, and we need to find when tangent is positive. Where does that occur? First quadrant, third quadrant. So what does that mean exactly? We need to find the pi over 3 families in those quadrants. Well, we already know 1, it's pi over 3, because that's here in this quadrant. But we also need to know the 1 here. So remember, this is 3 pi over 3. So if you go 1 more pi over 3, we get 4 pi over 3 as a result. So that means these are the answers to the problems. And take note, I didn't mention this in the first one, but you can just literally take these expressions and put them into x and check your work if you wanted to. And everyone should be able to do basic trig evaluation, so feel free to do that to check your work and understand the solution to the problem. Okay, so moving on to 3. This time we have 4 sine squared minus 3 is 0. So we have a unique new addition to the problem of a squared term. Okay, so let's not get too intimidated. We still are going to have to solve for the sine of x, but for now, just like if I was given this, Okay, we wouldn't do anything with that x squared until we get it by itself. We would need to take care of the negative 3 and the 4 beforehand. So let's do that. So we want to add 3 over to the right, and then we want to divide by 4 in order to get 3/4. Okay, once we get to this step, we still haven't gotten a single sign x, sign to the first x. We still have a sign squared. So just like if I had done the same thing over here and gotten x squared is equal to 3/4, what would we do in the next step? We would clearly take the square root of both sides. So we're going to do the same thing here. Square root of both sides. Now we're going to get sine x over here, but this is the key that usually almost a quarter, a third, even a half of the students blow this. Remember, you must put the plus or minus. If you don't, it's going to create a lot of problems. You're actually going to miss out on some of the solutions. Okay, but if you look at right now the square root of 3/4, that doesn't look like any special angle that we know, any special ratio that we know. But if we do a little simplifying of that, we're going to get the square root of 3 over the square root of 4, which is 2, and then all of a sudden we have this expression, which is very familiar to us. Okay, so once we get this expression, the key is, again, what are we dealing with? Well, remember, sine is the y-coordinate, right? So we're looking for a y-coordinate of root 3 over 2. Remember, that only occurs when the x-coordinate is a half at pi over 3. So we're dealing with the pi over 3 family. So we're looking for when the result of a pi over 3 family is plus or minus. Okay, so that's weird. So let's look at this. All students take calculus. So when is sine in the scenario, when does that create a positive result? Well, that creates a positive result in here and here. Well, where does it create a negative result? It creates a negative result here and here, which means we actually have 4 solutions to our problem. 4. They want the pi over 3 family radian value in every single quadrant. Well, in quadrant 1, we know it's pi over 3. Quadrant 2, 2 pi over 3. Quadrant 4, 4 pi over 3. And if we go all the way to quadrant 5, it is 5 pi over 3. So the answers to the problems are all 4 of these results. So just as a side note, though, what if right here you forgot the plus or minus? You would have just gotten a plus root 3 over 2, which means you would have completely missed out on the final 2 solutions that create the negative, and you would have only given me pi over 3 and 2 pi over 3. So one of the big things in this section, if you see a squared and you end up isolating it, realize you're going to be working with 4 solutions. Okay, so let's try another problem in that genre just to make sure all is going well. So for number 4, we have the cosecant squared minus 2 is equal to 0. So this is our first reciprocal trig function, but don't let it scare you. You know how to handle reciprocal trig functions. Ideally, we don't want to deal with that now. We want to first just isolate it before we go anywhere. So makes sense that we're going to add the 2 over to the right side. So at this point, we know that the cosecant squared is equal to 2. So that means that the sine squared should be equal to the reciprocal of the right side, which is 1 over 2. So this is a critical step that you want to be very careful of when you're doing it, but realize that is the case. So, again, we're in a squared problem, so we need to take the square root of both sides. What are we going to get? We're going to get the sine of x is, again, plus or minus root 1/2. Now, this one is not as nice. Why is that? Well, as an aside over here, root 1/2 is the same as root 1 over root 2, which is 1 over root 2. But, again, that is not a special ratio we know of. That's because it needs to be rationalized. We're going to get root 2 over 2, so the sine of x is equal to plus or minus root 2 over 2. So again, what are we looking for? We're looking for when the y-coordinate is root 2 over 2. We know that occurs when the x-coordinate is root 2 over 2 as well at the pi over 4 families. So what do we need? We need the pi over 4 families wherever sign is positive or negative, all right? So if you look, again, sign is positive first two quadrants, negative second two quadrants. So that means we need all of the pi over 4 results for our solutions. What are they? Pi over 4 first quadrant, 3 pi over 4 second quadrant, 5 pi over 4 third, and finally 7 pi over 4 in the fourth quadrant. And those are the solutions to our problems. Okay, so I would classify the problems that we've worked on so far up top here as the easier problems. Why? Because you basically go right to the solution. You get to this step very quickly. But there are problems where you are going to use a little bit more advanced algebra in order to figure them out. Usually those are the problems that have multiple trig functions in them. Sometimes they are similar trig functions like in 5. Sometimes they're different, sine and tangent number 6. But they should resemble to you algebra problems, or at least eventually they will. So if you look at number 5, basically what we have is a scenario where we have a sine squared, we have a sine to the 1, and then a constant term. So the best way for me to really help you decipher what you're looking at here is this is essentially identical to this. We have a quantity squared in the beginning, we have a quantity not squared, and then we have a constant, which is basically a trinomial. So all this is factoring a trinomial where the constant in front of this leading term is not 1. So what do we normally do when we factor a trinomial? We set it up like this, correct? So these have to be 2x and x. Because this is a positive 1, that means that these signs have to be the same, but because this is a minus in the middle, they have to be 1s, and we end up getting this as our factored expression. So then we go over to our other problem, our actual problem. We go, oh, okay, so that means this is going to be 2 sine x minus 1, and this is going to be sine x minus 1. So you can see, hopefully, as you go back and forth between these two equations right here, you can see that all we're doing is algebra, but we're doing it with trig functions inside, or sort of inside that trinomial that you're working on. So where do we go from here? That's the question, right? Well, what would we do over here? We would set both of these equal to 0 and solve. Well, we don't do anything different on the other side. So we need to set 2 sine x minus 1 equal to 0, and we need to set sine x minus 1 is equal to 0. So what basically happens? We end up with 2 trig equations. So I know that sounds intimidating, but it is what it is. We now have to solve 2 trig equations and get the answers to both of them as our solutions. So let's do the right one first because it's easier. So this, if we add 1 over, we get sine x is equal to 1. So if we're looking at where the sign is 1, then if you're looking at, let's say, a unit circle, hey, look at this, I have a unit circle over here, what am I doing? So we're looking for when the y coordinate is 1. Well, where's the only place that happens? Up top here, where it's 0, 1. So where is that? What rotation is that? That's at pi over 2. So a solution to our entire problem is pi over 2. So if you put pi over 2 in here, both sides would be the same. But we're not done. What about the other side? Well, add 1 over, divide by 2, and get sine x is equal to positive a half. So again, what are we doing here? We need to find when the y coordinate is a half. Well, that we know that happens when the x-coordinate is root 3 over 2 in the pi over 6 family of angles. So we need to know when sine is positive, which is in, again, the first 2 quadrants. So what are the solutions for pi over 6 in those quadrants? Pi over 6 and 5 pi over 6, which means the ultimate solutions to our problem are all of these. So pi over 6, 5 pi over 6, and pi over 2, and you would list all of them as a result, and all of them can be checked by just subbing them into there and getting the result. Okay, another algebra-based equation that we need to solve. So this is a very tricky. So let me just rule this out right away, because what will students do in this problem that will absolutely destroy it? They'll look at both sides and say, I want to divide sine x from both sides. Do not do that. Just like you cannot divide variables. For example, if you had like x squared is equal to x, you cannot divide both sides by x. That is illegal when you're solving an equation. So don't do that. So the key is in this scenario is you basically need to be able to use algebra to figure this out. So what would you do? Well, normally in algebra problems, just like this one up here, is what was on the right side of the equation? 0. Well, we want to do the same thing here. We want to get this sine x over to the left side by adding it. Okay, so this is, even when students get this, they still struggle with this because they just don't see the algebra, but hopefully you see that this is a classic GCF problem. The greatest common factor of both these terms is sine x, so let's factor out a sine x and get sine x times tangent x plus 1 is equal to 0. So what do we have? We have a scenario, again, just like here, right here, where we have two quantities multiplied equal to 0, which means we set both of them equal to 0, right? Which gives us two equations to work with. Ooh, that's a new color. Two equations to work with, and we just solve them. So look at the first one. Sine x is 0. So we're looking for when the y coordinate is 0 on the full spectrum of 0 to 2 pi over here. So where does that occur? At 1, 0 and negative 1, 0. Well, what are those solutions? They are 0 and pi, which means 0 and pi would be the answers to this side. Over here, we have tangent x is equal to negative 1. Similar to some of the problems we did before, how do we produce a tangent of 1 to start? Well, that only occurs y over x when it's root 2 over root 2, which is at the pi over 4 family of angles. But we want to know where this occurs, where tangent is negative. So it's positive in 1 and 3, which means it's negative in 2 and 4. So what are the pi over 4 families there? They are at 3 pi over 4 and 7 pi over 4, which are here and here for pi over 4, which means if we want to write this whole thing as a solution, we would write 0 pi, 3 pi over 4, 7 pi over 4. And that would be this. Those would be the solutions to our problem. And again, we could sub them in here just to check to make sure those are right, and you would be able to get what you need. Okay, so number 7 here is a doozy. Okay, so why is it a doozy? Just because there are times where identities might appear in your trig equations. I don't tend to give a lot of those just because they can be quite challenging to follow, and solving equations is often hard enough, but it's not going to rule it out appearing on like one of the exams or something like that, or in a lab, so you need to be able to locate this as you go. So what's a good hint? Well, if you look at this problem, interestingly enough, we have a sine squared and then a cosine. So in these problems, this problem over here, we had a sine squared and a sine, which means they were of the same ilk or variable or type of trig function. Now we don't. There's literally no way you're going to solve a problem like this unless you find some way to turn one of these into the other. So find some way to turn cosine into sine or sine squared into cosine squared. Well, hopefully me just saying that is ringing a bell for you, because you guys already know, you guys already know how to change that. You already know that sine squared and cosine squared have a very clear relationship as follows. Pythagorean identity right here, right? So we should be able to solve for sine squared and get 1 minus cosine squared, and then take this and plug it into there. So let's do that. So we're going to get 2 times 1 minus cosine squared minus 3 cosine x is equal to 0. Okay, we're going to do a little distributive property here. And then basically what we have now is essentially what we had in this problem. Squared, a single sign term in that one, and a constant. This time we're going to have a square cosine, a single cosine, and a constant. But remember, when we did problems that were trinomials, we never wanted that leading term to be negative. So what I'm going to do is I'm going to multiply everything by a negative. So negative 2 plus 2 cosine squared x plus 3 cosine x. So multiply by a negative 1 here. And then I'm going to rearrange this sucker so that it looks just like the problem that we were working on before, which looks like this. Okay, so now again, where are we? This is very similar to something that would look like this. 2x squared plus 3x minus 2 is 0. Okay, so if we were to factor that, what would that look like? Well, again, it would have to be 2x and x. The other two numbers would have to be 1 and 2. Because this is a negative, that means the signs are opposite. So we would have to do a little sort of trial and error here in order to figure out how we can grade a positive 3 as a difference. Well, you would do that by making this 2 and this negative 1. So once we get that, we can return to our problem and go, okay, well, what would that be here? Well, x is cosine. So we would do cosine x, 2 cosine x minus 1, and we would do cosine x plus 2 equals 0. Okay, so these are our two equations now. Just like before, we want to split them up, so we have 2 cosine x minus 1 is equal to 0, and cosine x plus 2 is equal to 0. If we solve for cosine x to isolate it in this one, we're going to get a half. So how do we find that? Well, we're looking for the coordinate where we have the x coordinate is a half, which means the y coordinate is root 3 over 2, and this all occurs at pi over 3. Any family of pi over 3, so we want anywhere where cosine is positive. Well, that occurs at quadrant 1 and 4, so that creates pi over 3 and 5 pi over 3 as the solutions. So far we're there. Now look at this guy over here. This is interesting. If we solve this, we get cosine x is negative 2. So hopefully this is absolutely creating like a gigantic red flag right now. Why? Because the range of possible values for cosine only exists. So remember on the graph for cosine, they were negative 1 to 1, right? So it was something like this. It was something like that. But the range of values only goes up to 1 and down to negative 1. We can't even get to negative 2. So this is actually no solution. Okay, now I know students will struggle with this a little bit because they're so used to like just quickly doing ratios, but if you get a number as an answer to cosine, a ratio that is above 1 or below negative 1, there is no solution for that, which means all you do is write out this by itself as the solution for this problem. Okay, so the last element of this section, so basically this is kind of like a break in the lesson a little bit. The last part of this section is about what happens when you have to solve a double or a triple or even a half angle in a trig expression. Okay, so just to be clear, this is challenging because it's not what you would expect it to be. So for example, what is the first thing that students do when they see tangent 2x equals negative 1? And I see it on exams all the time because students don't really study this well enough. But what they'll do is they'll divide both sides by 2 and get this. That is absolutely dead wrong. Okay, you cannot do that. If this 2 is in here, that means it is owned by tangent. You cannot remove it from that scenario, which means this entire concept, which students will, it's a logical thing to do. It's not, I'm not like angry when I see it or anything like that. It's very logical, but it just doesn't work in trigonometry, which means you need a new way in order to figure out how to do that. So, I'm going to give you a bulleted strategy for figuring this out. It can be very simple as long as you follow the strategy exactly the way I set it to be. Okay, so just to be clear, starting here, it says, therefore the goal will be to be able to solve this equation and any multiple equation in the following manner. So we're going to start here. First thing you do is extend the range of the resulting solution to the exact multiple that the angle suggests. For example, since we have a double angle, we double the original range. So what was the range of values? Well, for tangent x, it was from 0 to 2 pi. So for tangent 2x, we're basically going to go for 0 to double 2 pi, which is 4 pi. Okay, that's the first sort of setup. So just to be clear, if it was tangent of half x, it would be 0 to pi. If it was tangent 3x, it would be 0 to 6 pi, and so forth. You just extend the range of possible values to that. That's the first thing. Then what do? You solve the equation as if the double, half, triple, whatever angle it is, you solve it as if it wasn't there. So we're going to solve, instead of 2x equals negative 1, we're going to do tangent x equals negative 1. So if you recall, we actually already solved this somewhere along the line. Yeah, so here. So we solved that the tangent of x equals negative 1 is 3 pi over 4 and 7 pi over 4. So 3 pi over 4 and 7 pi over 4. Why do we know that? Because the tangent is 1 at pi over 4 families, and we want it to be negative. So hold on a second. That only occurs at these two quadrants at 3 pi over 4 and 7 pi over 4. But the key is we're doing that over the new range. So note, 0 to 4 pi. So 3 pi over 4 and 7 pi over 4 is only from 0 to 2 pi. This is saying we need to go around again and generate solutions. So what does that look like? Well, this can be sometimes a little bit of a struggle for students, and I get that. But what are you basically doing? Well, if you are at, let me write this in very emphatically here. So if we're at 3 pi over 4 right here, if I need to go around again and come back here, that's a total of 2 pi. So all I have to do is do 3 pi over 4 plus 2 pi for the next solution. If I was doing the same thing for 7 pi over 4, then I would be here. And if I need to go around again, I have to add 2 pi to that and get 7 pi over 4 plus 2 pi. So just to be clear, all I'm doing is finding the next rotation around the circle if I had to go around again, which is the purpose of this problem. So what am I getting if I do that? I get 3 pi over 4 and 7 pi over 4, our original angles. But I also get the next iteration of that. So again, remember when we do common denominators here, what's 2 pi the same as? It's the same as, in this scenario, 8 pi over 4. So we're going to do 3 pi over 4 plus 8 pi over 4 is 11 pi over 4. And then again, 7 pi over 4 plus 8 pi over 4 is 15 pi over 4. Okay, so just to be clear, this is part of a process, right? So these are not the solutions to the problem. They are the solutions to this problem. So the big thing is, the next step is, how do we get back to how do we actually find the solutions to the original problem, tangent 2x is equal to negative 1? Well, we do just this. All we do is set the angle 2x equal to each one of our current solutions, as such. Then we treat them as each one of them as a separate equation. So how do we solve for x? We divide both sides by 2. Remember, If you divide by 2, it's the same as multiplying by the reciprocal of 2 of a half. So then we're doing 3 pi over 4 times a half, which is going to give us 3 pi over 8. And we're doing the same thing for all of them, which would be the equivalent of changing all the denominators to 8. Okay, so the answer to our problem in this scenario will be 3 pi over 8, 7 pi over 8, 11 pi over 8, and 15 pi over 8. I always thought of this as a very straightforward solution, but you must understand the steps that you're going by. So just to reiterate, in our problem, what's the first thing we do? We extend the range of possible outcomes from our original 0 over 2 pi to whatever the multiple is here in our problem. So that'll change sometimes. I'll show you that later. Then we solve as if the multiple isn't there, right? But we do it over this new range. So not only do we rotate around the once for 0 to 2 pi, but now we're going to rotate again around for double that much. So that's where these guys came from. So then we take each one of these solutions and set it equal to 2x and divide by 2 and get the solutions to the original double angle problem. That is, we'll do 2 examples here to practice that, and then so that you can get a good idea of how to do it. Okay, so let's try another one of these. So this we do have a double angle here again. So let's try another double angle problem. Okay, so what are we basically trying to do here? So the first step is we need to solve cosine x, so ignore the double angle, is equal to -1/2 on 0 to what? Well, normally cosine x is to 2 pi. Because of this double angle, we need to double that, so we're going to 4 pi. So in essence, we're going around the circle, unit circle, twice. We'll cover that in a second. So basically, we start with what our solutions will be. So we have solutions to this. Solutions are, so let's find them. So what are we looking for? Well, we want the x-coordinate to be a half, which means the y-coordinate is √3/2. This occurs at the pi over 3 families. But we want it to be negative, which means cosine to be negative, which occurs here and here. So what are they? Those are 2 pi over 3 and 4 pi over 3. Okay, but that's only one around. We need to go around again. So as was talked about in the previous example, we can do that by just finding the next coterminal angle for each of them, which is an old topic. All right? Remember that 2 pi in this scenario, 6 pi over 3 is the common denominator. So we are going to get solutions of, this guy is going to end up being, it looks like 8 pi over 3, and this guy is going to be 10 pi over 3. So we currently have solutions right now, temporary solutions of those 4. Okay, so what is the strategy? So if you recall, once we got the actual solutions to the original problem, we go and we set 2x equal to each one of them. So essentially, what do we get? We get 2x is equal to 2 pi over 3. 2x is equal to 4 pi over 3. And we continue with all the other solutions as such. The last step is we divide both sides by 2. Remember, that is equivalent to multiplying by a half. So if we multiply 2 pi over 3 times a half, we could get 2 pi over 6, but why not cancel out the 2's and just get pi over 3? For this one, cancel out the 4 and the 2 and get 2 pi over 3. For this one, the 2 and the 8 would cancel. We would get 4 pi over 3. And then for this guy, we would get 5 pi over 3 as the result. So these are the solutions to the original problem. So just to be clear, if we actually took any one of these solutions and plugged it into the original equation, we should be able to check our work without any issues whatsoever. This is a very important step, and especially in these, that you check your work to make sure you didn't flub the math at all. But there are 4 solutions, and the ones in the box are it. Okay, so last problem in this section, and in chapter 5, by the way. So let's say we were solving a triple angle this time, right? So now we're in a really interesting scenario. So triple angle. So what does that look like? Our goal is we need to solve a single angle of the same problem. Sine of x is equal to negative root 2 over 2 on 0 to triple the range of possible values, which would bring us all the way to 6 pi. So in other words, 2 pi, 3 times 2 pi. Okay, so where are solutions? So solutions, actually, let's just put a different color. So solutions are, and there's going to be a lot of them. So let's start with the ones we know, going just one way around. So we are dealing with a y coordinate of root 2 over 2, which means our x is root 2 over 2 as well, which occurs at pi over 4. So but we want negatives, right? So this is a negative result here. So when is sine negative? At these two quadrants. So these two quadrants in the pi over 4 family are 5 pi over 4 and 7 pi over 4. Now, here's where things get tricky. We need to go around again. So you know how to do that. You know that you need to add 2 pi to each one of these to do that. Okay, but that was when we were going to 4 pi. We need to go around again. Another 2 pi, which means we need to take... Oh, this is, by the way, it's a typo. This is 7 pi. Okay. We need to go around again, which means we need to take the same 5 pi over 4 and add 4 pi to it. And the same 7 pi over 4 and add another 4 pi to it. So in this scenario, that's basically the idea, is that this time there will be 6 solutions to the problems. So let's just do a little bit of the math here. Remember in this scenario, 2 over pi is 8 pi over 4. So we're going to get some crazy answers. So let's start here. So this is going to end up being 13 pi over 4 when you do the math. This is going to be 15 pi over 4. This is going to end up being, so 4 pi. Let's get rid of this so I can write. So 4 pi is going to be ending at, when you do like a common denominator of 4, you're going to get 16 pi over 4. So that's going to be 21 pi over 4. And this is going to end up being 23 pi over 4. Okay, so we have now 6 solutions. What do we do with them? Now, we don't set 2x equal to them. That doesn't make sense. Each one of these problems were double angles, which is why we set 2x equal to them. Now we have a triple angle, so that is what we're going to set equal to each one. So 3x is officially going to be equal to all of these scenarios. So we can do this in a short manner. I have no problem with that. Instead of writing out 6 equations. Instead, if you want to write it like this, let's say, we can do that. So let's say 3x was equal to all of these in separate problems. What would we have to do? We would have to divide both sides by 3, which is the equivalent of multiplying, by 1/3. So we need to take all of these and multiply by 1/3. So what do we get when we do that? We get 5 pi over 12. We get 7 pi over 12. We get 13 pi over 12. Just be careful here. I don't want to be confusing. Okay, we get, looks like 15 pi over 12, which, by the way, can be reduced to 5 pi over 4. We get 21 pi over 12, which can be reduced to 7 pi over 4. And finally, we get 23 pi over 12. And those would be our 6 solutions. If you don't want to reduce them, it's not a huge deal. But I'm looking for making sure that you just get the 6 solutions that are of importance. And again, if you want to, you can take this and plug it right in there to confirm that you're going to get negative root 2 over 2 as the result for the problem.